Welcome to part 2 of our introduction to capacitors. Before we begin, there's a few things that we should remember. That a battery is a device that maintains a separation of positive and negative charges through chemical means. This separation of charge establishes a potential difference across a battery's terminals. We should also remember how we defined capacitance. The capacitance is defined as the ratio of charge per potential difference. We use the definition of capacitance to show that the capacitance of a parallel plate capacitor is equal to the product of the permittivity of free space and the ratio of the area of a capacitor plate to its diameter. We should also remember that the work used to charge a capacitor is stored as the potential energy in the capacitor. That potential energy can be expressed in terms of the ratio of charge to capacitance, or in terms of a combination of capacitance and voltage, or as a combination of charge and voltage. And finally, we should remember that energy density exists at any point in space where an electric field is present. So at this point, you're probably wondering, why is any of this important? There are a variety of applications in which we use capacitors in the everyday world. For example, the keyboard in which I use to prepare this lecture demonstration, such that you could read the text that appear on the screen right now, well, the keys use capacitors. In fact, the keys on most computer keyboards are just capacitor switches. Pressing the key pushes two capacitor plates together, increasing their capacitance. For example, let's say this is a key in a keyboard, and this might be the upper plate of a capacitor. And then here is the lower plate of the capacitor. When you press down on that key, that causes the plates to get closer together, thereby increasing the capacitance, registering as a keystroke. Another very common and necessary application of capacitors is computer RAM. The computer in which I am presenting this demonstration has quite a bit of RAM in it. Now, your computer's RAM, which is an acronym for Random Access Memory, uses tiny capacitors to store digital ones and zeros that make up your data. A charged capacitor represents a 1, and an uncharged capacitor a 0. For 1 billion or more capacitors to fit on a single chip, they have to be very, very small. The micrograph here that you see is a cross-section through the silicon wafer that makes up the memory chip. Each capacitor here consists of a very long electrode separated by a thin insulating layer from the common electrode shared by all the capacitors. Now in this depiction, each capacitor's capacitance is only 30 times 10 to the minus 15th farads, or 30 femtofarads. That's extraordinarily small. Now there are a variety of other uses for capacitors, such as regulating the heart rate in someone's heart that has a pacemaker installed, or controlling the timing of intermittent windshield wipers, or even tuning into an AM radio station. These different devices require capacitors. Very important. So with that said, it's probably a good idea for us to study some of the properties of capacitors. The first thing you should know is that multiple capacitors in series may be replaced by a single capacitor, called an equivalent capacitor. So let's say we have a series of two capacitors here. We'll call this first capacitor C1 with capacitance C1, and here is C2 with capacitance C2. These two capacitors can be replaced by a single capacitor that represents some combination of the original two capacitors. We're going to learn what that combination is. The thing about capacitors in series is all capacitors in series have the same magnitude of charge on each plate, equivalent to the charge of the equivalent capacitor. Well, let's look at that in this situation. So here's our two capacitors in series, capacitors C1 and C2. Well, capacitor C1 has a charge of plus Q1 on its positive plate, minus Q1 on its negative plate. Capacitor C2 has plus Q2 on its positive plate and minus Q2 on its negative plate. Well, because these two capacitors are in series, the magnitude of charge on capacitor 1 is equal to the magnitude of charge on capacitor 2. And these two magnitudes of charges are equivalent to the charge of the capacitor that we could replace capacitor C1 and C2 with, our equivalent capacitor. The moral of the story: all capacitors in series have the same magnitude of charge on each of their plates. Another property of capacitors placed in series is that the potential difference of the equivalent capacitor is equal to the sum of potential differences of each of the capacitors in series. Now, we know this from our brief introduction to circuits. Because of conservation of energy, we know that the potential energy at various points in a circuit may be summed up. And since electric potential is defined as the potential energy per charge, we could say that the electric potential difference between 2 points added to the electric potential difference between 2 other points will equal to the total potential difference between those pairs of points. For example, let's look at these 4 points. We'll label this first point A, the second point B, the third point C, and the fourth point D. These capacitors are in series because each one of these components share a single point with another component. Now, for capacitor C1, we have the potential difference across C1, which I'll call the potential difference V1, is equal to the potential at point B minus the potential at point A. Another way of saying that would just be the potential difference from A to B. If we were to look at the potential difference across capacitor 2, here's capacitor 2, we'll label that potential difference delta V2. And that potential difference is just the difference in potential between point C and point B. Also, we could refer to that as the potential from B to C. And then for capacitor 3, it has potential difference V3, and that potential difference is just the difference in potential from point D and point C. And we could refer to that as the potential from C to D. So if we are replacing these 3 capacitors with a single capacitor, the only thing we have to do is just sum the individual voltages to get the total voltage from A to D, or the potential difference across that entire series. And that potential difference from point A to point D is, remember, just the sum of V1 and the potential difference V2 across capacitor 2 and the potential difference V3 across capacitor 3. The potential difference across capacitor V1 is the difference between the potential at B and the potential at A. The potential difference across capacitor C2 is the potential difference between point C and point B. And the potential difference across capacitor 3 is just the difference in potential between points D and point C. And from here, notice the potential at point B cancels with negative the potential at point B. The potential at point C cancels with the negative of the potential at point C. And we're left with the potential difference of the equivalent capacitance of the equivalent capacitor formed from the three capacitors in this series is equal to the difference in potential between points D and point A. And that was just given by the sum of the potential differences across those three components. So in summary, the charge on each capacitor in series is the same. And that charge is the same charge as the charge on our equivalent capacitor. While the potential difference of each capacitor in series sums to the total potential difference of our equivalent capacitor. With that said, we can show the reciprocal of the equivalent capacitance of the capacitors in series is equal to the sum of the reciprocal capacitances. Well, let's take our three capacitor combination. Now, we could generalize this to more than three capacitors, but let's just use these three since this is what we've been working with. Each of these capacitors has its own capacitance that can be different. C1 is the capacitance for capacitor 1, C2 is the capacitance for capacitor 2, and C3 is capacitance for capacitor 3. And each one of these, since they are in series, we know each of them have the same magnitude of charge. We also know that these three capacitors can be replaced by a single equivalent capacitor. Now we know that the single equivalent capacitor has the same amount of charge as each of the individual capacitors in series. And we also know that the single equivalent capacitor has a potential difference equal to the sum of the potential differences of each of the capacitors in series. Well, let's start with the potential difference of the equivalent capacitor. So the potential difference of the equivalent capacitor is equal to the potential difference across capacitor 1 plus the potential difference across capacitor 2 plus the potential difference across capacitor 3. Let's remember, Valley College is quaint. This is a relationship that we have between potential difference, the capacitance of a capacitor, and the magnitude of charge on the capacitor. If we rearrange this, we would see that the potential difference across a capacitor is equal to the ratio of the charge on the capacitor to the capacitance. Let's use this relationship to express our potential difference in terms of charge and capacitances. So the potential difference of the equivalent capacitor is just equal to the ratio of the charge on the equivalent capacitor over the equivalent capacitance. Now, we know that that charge on the equivalent capacitor is equal to the magnitude of charge on each of the individual capacitors. The potential difference across capacitor 1 is equal to the charge, the magnitude of charge on capacitor 1 over capacitor 1's capacitance. And just like with the equivalent capacitor, that is just equal to Q, the charge that's on each of the capacitors, over the capacitance of capacitor 1. This holds true also for the potential difference across capacitor 2, being equal to the ratio of the charge Q to capacitor 2's capacitance, and also for capacitor 3. The potential difference across capacitor 3 is equal to the ratio of the charge that is on each of the capacitors over capacitor 3's capacitance. So with that said, we can take the relationship that the equivalent voltage is equal to the sum of the potential differences of each of the individual capacitors, and we could express this in terms of the charges and the capacitances. For the equivalent potential difference, we have Q over the equivalent capacitance. For the potential difference across capacitor 1, we have Q over C1. For the potential difference across capacitor 2, we have Q over capacitor 2's capacitance. And for the potential difference across capacitor 3, we have Q over capacitor 3's capacitance. Now notice there is a Q, a charge, in each term. And so those charges cancel. This leaves us with the expression that 1 over the equivalent capacitance is equal to the sum of the reciprocal capacitances of each of the capacitors in our series combination. Now this can be generalized. We did this for 3 capacitors, but really, we could find the reciprocal of the equivalent capacitance of the equivalent capacitor for any number of capacitors in series. And that is just equal to the sum from I equals 1 to n of the reciprocal of the capacitances. And so if we want to know the actual equivalent capacitor, so if we want to know the actual equivalent capacitance, we just take the reciprocal of this. This allows us to write that the equivalent capacitance of a combination of n capacitors in series is equal to the reciprocal of the sum of the reciprocal capacitances of each of our capacitors in series.